Welcome everybody to another week of Chilloquium. It's really exciting to see everyone here today. To start off, I'll just go over kind of what to expect. So we want this to be somewhere between a seminar and a lecture. We want it to be a really relaxed environment where you feel comfortable asking whatever questions come to mind. So we really encourage you to ask questions. You can raise your hand in the participants window, or you can message questions into the big chat, or you can send them to Sambuda and I individually, and we can ask them for you. Otherwise, just try to stay muted when you're not speaking so we don't get background noise. And we really encourage you to turn on your video so that we feel like we're all in the same room together and close some of the real life distance. But other than that, I think Sambuda is ready to introduce today's speaker.
Yeah, so before I do that, we just want to say Chris and I have been hosting this. This is the 35th one that we've had, I think. And we're very lucky to have had this sort of platform and such a wonderful audience. And while this is the last one that we're foreseeably doing, we're just very thankful for the opportunity to do this. So as our final speaker for this year, we thought like most appropriate choice would be Professor Georgi, who welcomed both of us into the department 4 years ago. And so we're very excited to have Professor Georgi today. He really needs no introduction, plus he's going to introduce himself in a second. But I'll introduce him by way of a very interesting fact. Professor Georgi had a boa constrictor as a pet when he was a child. This is kind of incredible to me, but the boa constrictor was only 8 feet. So if you're thinking about how the logistics worked, this is how I rationalized it. And it was a surprise Christmas present, or a surprise present, maybe not Christmas, and it was introduced to his family when his mother, as surprises go, wrapped it around herself and put a coat over her to hide the boa constrictor. So without much further ado, Professor Georgi, thank you so much. Take it
away. Thanks, guys. As you can tell from that fun fact, I had a slightly strange family, but that's okay. I was told that I should give you some idea of how I got where I am, and I've probably overdone it, but I've created a short history here. I hope. Let's try that again. Okay, there we are. So I was born in San Bernardino, California. This may be too small, but you may be able to see a little red circle on the map. And I was born in 1947 in the post-war baby boom. My dad was a bomber pilot in the war and somehow managed to survive. And my mom was a housewife, though she was also an economics concentrator at Stanford. So she was a bright woman. And we moved around a lot because my dad got a job as a Band-Aid salesman for Johnson & Johnson. And so we moved every couple of years as he was working his way up through the company. So the first thing we did was to move to El Paso, Texas, which is, there it is on the map. And that's where I had my first dog. Then we moved to Denver, and that was before it was Denver. It was still a fairly little town, but that's where I went to kindergarten. We didn't stay in Denver very long, and we moved to Dallas. And that was well before Dallas was Dallas. I'm sure the open field where I lived is now covered with huge buildings. But that was kind of interesting. Then I moved back to Southern California, first to Pasadena, and actually very close to Caltech and the Rose Bowl, and then to West Covina, and that's where actually we had the boa constrictor in Pasadena. In Covina, we had a couple of raccoons, a monkey, and innumerable cats and dogs, of course. And then we moved cross country back to northern New Jersey, which is where I went to junior high school and high school. And by that time, we were close to the headquarters in New York, and so we could stay put until I went off to college. So my family I'm the only scientist in the family. As I said, my dad's a salesman, my mom was a housewife. But I think my mom encouraged me to do sort of interesting mathematical things. And one of my earliest memories is learning about folding paper and cutting it into symmetrical shapes. So this is a picture of a snowflake of the sort that I used to make with my mom when we were in the little living room in Dallas long ago. Of course, I went through a dinosaur stage. I don't know if this book still exists, The Golden Treasury of Natural History. It's quite a beautiful book. My youngest son, by the way, never outgrew it. He's a paleontologist and still messes with dinosaurs all the time. And his children, I don't know what they're going to do because his house is covered with every kind of dinosaur paraphernalia. I'm embarrassed to say that I don't remember the wonderful chemistry book that got me interested in chemistry in second grade. And it was brilliant. First of all, it was understandable more or less to a second grader, organized around the periodic table. But what made it fun was that each of the elements was described in terms of sort of how you found it, how you mined it, how you refined it, and then what it was used for in industry. So it was a great book. And unfortunately, I can't remember the name. So if anybody happens to know, run across that book, let me know, because I'd love to find it. I've done some searching and have been quite unsuccessful in locating it. It was actually a great time to be a science kid. Even though my family knew nothing of science, science was in the air. Sputnik launched in 1957, and the physicists still had a lot of influence in the government because they had such an effect on the war. And it was also fun because science was different. Electronics was large enough that you could actually see and build things from scratch. It wasn't all integrated circuits. There were vacuum tubes and that were fun. They lit up and you could actually make stuff out of them, and there were transistors. And you could take stuff apart, and it was actually interesting. That's, I think, one of the things that I miss most for my grandkids. It's no fun to take anything apart anymore. But for some reason, my parents let me take apart a large television set. And I mean, this was nuts because I could have been injured seriously if I'd broken the CRT, which was this hulking thing. But the most fun was the speaker, which was a huge old-fashioned vibrating cone, as you still occasionally see. But the inductance was such that you could plug it right into the wall and hear the 60-cycle hum. So these things, it was really fun. So I miss having stuff like that. And there was no Consumer Protection Agency. So chemistry sets actually contained chemicals. That's another thing that saddens me about my grandkids, is that I can't legally give them an interesting chemistry set. But of course, I was a theorist from the beginning. Then as now, the stuff I built didn't actually really work very well, and it usually broke. And I would have given anything to play with some of the computer stuff that is now available, but I had to do all of this by myself. If I wanted to multiply something, I either used a table of logarithms or a slide rule. That's a slide rule, which is basically just an analog table of logarithms for use in multiplication. I learned calculus from the Encyclopedia Britannica, which is not an ideal situation, and then practiced by drawing graphs on actual graph paper. And it was fun, but this took a lot of time, and I really would have appreciated Mathematica in those days. So I was a nerd, still am, but I was even more of a nerd in those days. And I always assumed that I'd go to Caltech or MIT for college. But fortunately, some college guidance counselor told me that I should visit Harvard when I visited MIT. And I did, and I found the Harvard students much more interesting than the MIT students. So that is why I went to Harvard instead of MIT. It's frustrating this year because I tell that story whenever I'm talking to a free frosh, that if they're trying to decide between Harvard and MIT, it's really easy because the physics departments are both good, but what you do is you go and spend time with the students at MIT and the students at Harvard, and then if you like MIT better, you should go to MIT. But the students can't do that this year, and so I'm very curious to see what's going to happen and how that all plays out. So anyway, I got to Harvard and immediately did something stupid, which was to skip the course, which was the analog of Physics 16. It was at that point something called Physics 13. And it was taught by an absolutely wonderful man, Ed Purcell, who was won the Nobel Prize for discovering nuclear magnetic resonance. But it wasn't, there are Nobel Prize winners and Nobel Prize winners, but he was really a good Nobel Prize winner. And he just had a wonderful way of thinking about physics. Some of that I hope that many of you have seen in the electrodynamics book, which is just such there's so many thoughtful discussions of what the physics is. That was the way Ed was. Anyway, I skipped it and I took instead Physics 112, which was sort of the equivalent of Physics 16, of Physics 15C rather. And it was pretty terrible. The teacher was an aging experimenter, Ken Bainbridge, who was involved in the discovery of the muon. He was a pretty famous guy, but he read from a textbook in lecture, and this didn't impress me too much. So I pretty much stopped going to class. Fortunately, we had a really good TF who noticed that I was incredibly bored and gave me this book by Richard Feynman, Theory of Fundamental Processes. And the good news is that I was learning some quantum mechanics in my chemistry classes. It's amazing that I became a physicist because I had really great chemistry classes and terrible physics classes my first year. But between the quantum mechanics and chemistry and this book, and the fact that it was an interesting time in particle physics when Gelman's symmetry arguments had just surfaced, and we were beginning to make sense of the zoo of particles. That I just fell in love with particle physics basically that first year, because I knew enough quantum mechanics to see how it might apply to this little tiny world of elementary particles. So that was fun. Some of the other faculty who were around were Norman Ramsey, who is possibly the nicest Nobel Prize winner of all time, and Julian Schwinger, who was got his Nobel Prize when in my junior year. No, sorry, my sophomore year, which was pretty exciting. So I thought he was probably the leader of the group. That was completely wrong. The leaders of the theory group were Sidney Coleman and Shelley Glashow. And nevertheless, I took Schwinger's 253 class, which should have been quantum field theory, but it wasn't, because by that time he'd given up on quantum field theory and was teaching source theory instead. But fortunately, I also took Sidney Coleman's group theory class. And one of my, along with not being able to find my chemistry book that I mentioned, two of my greatest disappointments have to do with things that my mother threw away. One of them was my Pickett slide rule, which was just classic. And the other was my notes to Sidney Coleman's group theory class. And there's still 50 years later, things that I think Sidney did more elegantly than I can reconstruct. So that was hard. I also got very lucky because I had, by this time, figured out that by my senior year, I figured out that the really interesting physics was being done by Coleman and Glashow. And so I got up my courage in the fall and asked Shelley whether he would give me a reading course on particle physics. And of course, Shelley said, yeah, because Shelley was, it wouldn't have been a very good course. But worse than that, it would have been a disaster. Fortunately, I was not allowed to take it because the deans told me I had to take another social science class instead. And so I took a course in abnormal psychology, which has stood me in good stead over the years. But more than that, it saved me from having to work with Shelley at an impressionable time, which would have just been a disaster because he's a little hard to deal with. Fun, but difficult to deal with. And that was me, of course, back in those days. Obviously, I haven't changed a bit. Okay, let's see. There we go. So I went off to Yale for graduate school, which was an odd thing to do because it was, in those days, a fairly sleepy little place in particle physics, a great university in many other ways, of course. But the love of my life was a student at Vassar. And I was really tired of driving all the way down the Mass Turnpike and turning left and driving some more to get to Poughkeepsie. And Yale was way closer. So that was the reason for that decision. And we've been married for almost 52 years, so that turned out to be a good choice. But more than that, it was a good time to be away from Harvard because for the most part, people at Harvard were depressed while I was away at Yale. And it's a funny time. A naive history records 1967 as the birth of the Standard Model, because that's when Steve Weinberg wrote his paper called A Theory of Leptons. In fact, nobody understood Steve's paper, including Steve. I remember getting this paper when I was a graduate student. In those days, of course, the papers arrived in the mailbox with physical review letters, and I looked at it, and it didn't look renormalizable to me, and almost everyone else had the same view. And Steve went on and just did other things for 3 years because he didn't understand how to make sense of it either. The one interesting thing that was being done at Harvard at the time was that Shelley with John Iliopoulos and Luciano Maiani, a couple of amusing characters, were made the convincing case for the existence of the charmed quark. And that is really interesting. Their mechanism, called the GIM mechanism, is it's only today that we're starting to see things that may be violations of the GIM mechanism. Would be incredibly exciting, because it's been an annoying fact about the world that we can't get rid of now for almost 50 years. But anyway, I had a fun time at Yale. I learned some quantum field theory from Charlie Summerfield, who was a student of Schwinger's. And fortunately, just about the time I was getting ready to leave to get my degree, Gerard de Tuft, who was just my age, another graduate student, explained everything. And the real birth of the Standard Model was at the end of 1970, when de Tuft came up with a simple explanation that everyone could understand, that Weinberg's model really made sense. And that was a perfect time to get started with my serious research career, because what de Tuft had done was to suddenly make sense of non-abelian gauge theories and spontaneously broken non-abelian gauge theories. So that meant that there was a whole new world of theories that hadn't been accessible before, or at least hadn't made sense before, that we could now play with. So I was in the right place at the right time. I was very fortunate to get a postdoc offer from Harvard, and even more fortunate that when I arrived, there was a fantastic group of young people there to play with. Tom Appelquist, David Politzer, who eventually won the Nobel Prize for asymptotic freedom, Eric Weinberg, unrelated to Steve Weinberg. Murray Gell-Mann used to call Eric the real Weinberg for some reason, just to annoy Steve. Joel Preback, Helen Quinn, who is a fantastic person, the mother of the axion, she's sometimes known as, and me. By that time, I'd grown a beard, so I didn't look 14 anymore, maybe 17, I don't know. I was their seventh choice as a postdoc. That gives you some idea of how depressed Harvard was at the time. Most people decided that the really interesting physics was going on elsewhere, in Seattle or someplace else. I learned that I was the seventh choice from the eighth choice, who was a fantastic character named Alvaro de Rucola, who was one of my really good friends in the business. Alvaro is a Spanish marquis. His father was the last hereditary heraldor of the Spanish court. And Alvaro is so good at everything, trained as a member of the Spanish nobility, that he makes pretty much everyone to uncomfortable just to be around. But we had a wonderful time, and he gleefully told me that he was I was the seventh choice because he was the eighth choice, and he arrived next year and completed this wonderful group of young people. So the moral of all that is that it pays to be lucky and to be at the right place at the right time. So I will eventually talk about some physics, but I first wanted to sort of look back on my career and mention the fact that while I've been in particle theory all my life, I've worked on, and I hope contributed to, lots of very, very different areas. And as I say, I hope dilettante is not the right word. But I don't like beating a problem to death. I like to learn something, make a contribution, and then move on to something else that's interesting. And my former colleague, Sidney Coleman, used to call this guerrilla physics. He liked to do the same thing. And the other comment, similar comment, is that I've only had one employer in my life. I took my first job at Harvard and have stayed there ever since. But I've had many, many careers. And that's an important thing to remember as you plan your own life. Careers are not the same as employment necessarily. I started out as a postdoc and then a junior fellow. And that was wonderful because in those days, those were carefree days when all I had to do was to do physics all the time. And it was a perfect time to do it because it was the time when our group was really one of the leading groups in building the standard model. So that there's lots and lots of interesting things that happened in those days, including grand unification, which ultimately got me my job, but lots of things that were equally fun. I think perhaps the even more fun in some ways than grand unification. Well, it's hard to be more fun than that, but the understanding why the sigma baryon was heavier than the lambda baryon was also really cool, I've got to say. Just a lot of fun physics. Then I fortunately got a junior faculty job at Harvard and started teaching. And this was fun. I'd always known, I knew how interesting Harvard undergraduates were. But what I learned when I started teaching a mixture of undergraduate and graduate classes was how incredible the Harvard graduate students are. This is a truly amazing group. And I started tentatively to try to attract some of these graduate students to work with me. That's hard when you're a junior faculty member because they don't know whether you're going to be around next year. But a few brave souls took the plunge, and then when I did get tenure, I found myself besieged by really wonderful students. Again, this was in part good luck, because at this point, both Steve Weinberg and Shelley Glashow were at Harvard. This was before Steve went off to the University of Texas. And they had, everyone knew that they were the leaders in this area. They were going to get the Nobel Prize for the standard model. And so all the best graduate students wanted to come to Harvard and work with Shelley and Steve. And when they got there, they discovered that both Shelley and Steve are extremely difficult to work with. In fact, almost all of the students ended up working either with Sidney Coleman or with me. And so it was just absolutely fantastic. I hope this will work. I have a link here to my academic progeny on academictree.org. So I have literally hundreds of students and grand students and great grand students from this period of the 80s, where Eddie was the first one. He was the brave soul that started to begin with. And you know, a lot of these people I don't know. I was kind of embarrassed when Angela Olinto was elected to the National Academy this year, because I hadn't realized that she was my grand student. But anyway, I was once I figured it out, I was very proud. So it was an amazing group, including some fabulous women physicists. Oh, I should say that this one isn't fair. Peter Gallison, who's a historian of science, was also technically my student. And so I can't really claim any of his students as grand students because they're doing history of science. But Ann Nelson, who sadly was recently killed in a climbing accident, was just one of the most remarkable people I've ever met. And her husband, David Kaplan, the same. Lisa Randall, most of you know, was a student of mine. And Ann Nelson, who's now and Elizabeth Simmons, who's now no longer at Michigan State. She's now at UCSD as a dean, in addition to a physicist. And Sally Dawson. I hope Sally's there somewhere. Anyway, it's an incredible group, and I was just so fortunate to, through no particular fault of my own, having had these students foist on me. Then, of course, I became chair, and that's always a kind of inflection point in anyone's career, because there's some people that never become chair because everyone in the department knows what a disaster it would be if they became chair. But for people that are reasonably conscientious, becoming chair is a disaster for you, because people learn what you care about, and then you can't get out of it. For me, the biggest thing that happened as chair is that I learned that we had been torturing our women undergrads, and so I became a feminist on the spot, because this was just absolutely inexcusable. And I spent a lot of the next many years working on issues in the education of women and physics education in general, because part of what we were doing was encouraging students in the bad old style of learning where you sat by yourself in your closet and tried to figure out what your august professor was doing. And the most important thing we did in this period was to encourage students to work together, and and also pay attention, a little more attention to the students than we had been doing. So that was an important role, and it led me really to think about being a housemaster and faculty dean, and also head tutor in the department, along with David, without whom that job would be impossible, and also teaching Physics 16, which is, I've got to say, one of the most fun things about my career is that Physics 16 got immortalized in the fabulous musical Les Phys. So if any of you have not seen that, you should check it out. The version is on YouTube with subtitles. So if anyone doesn't know how to find it, let me know, and I'll pass that along. So the moral of that was that, I mean, there are many morals. One thing I learned was, because I had the opportunity to collaborate with so many incredible physicists, was that each one of them was different. And it's hard to imagine two minds that work more differently than Shelley Glashow's and Steve Weinberg's. They might as well be from a different planet. In fact, they're from the same neighborhood in New York City, but you certainly wouldn't know it to do physics with them. And so this is one of the things that's convinced me that diversity in physics is so important, because there are probably more ways of being a great physicist than we have seen so far. And the other thing was that I just had a lot of fun with these incredible people, and it was a good time. So I thought I should spend a little bit of time talking about physics. So let me, without getting deeply into quantum field theory, explain why I think that unparticle physics is kind of fun, or at least confusing. So actually, I had been studying unparticle physics in graduate school without realizing it, because one of the things that I spent a lot of time on in graduate school was the Turing model, which was relatively new then. It's an exactly soluble quantum field theory in 1+1 dimensions. I'll tell you some more about it in a minute. But 40 years later, teaching Physics 16 made me think about how confusing this theory was, because I taught my students that all of the energy and the momentum that we see in the world is bundled into these particles that obey the relation E squared is equal to P squared plus M squared, or putting this, you can put the C's back in if you want. And that's not the case in the Turing model. The Turing model is a very simple theory. It's massless fermions in one space and one time dimension. And a 4 fermion interaction between 4 of these fields. Now, the way field theory works, that means that the coupling, the constant that goes with this little Feynman diagram that describes the interaction, is dimensionless. So this is a theory with no classical dimensional parameter. So classically, it's scale invariant. As you probably know, as you may know, in quantum field theory, classically in scale invariant theory doesn't necessarily give you a theory that's scale invariant when you incorporate the effects of quantum mechanics and renormalization. But in this case, it's scale invariant. And in fact, this was the theory, or one of the theories that led Ken Wilson to think about scaling and the operator product expansion, and his way of thinking about quantum field theory, which has had an incredibly important effect on what we do, not just in particle physics, but in condensed matter physics and other areas as well. So this was a theory, a quantum theory with no mass and no particles. And in fact, it's what we would now call a conformal field theory. It's got not just scale invariance, but conformal invariance, which is an extension of Lorentz symmetry to include scale invariance. Now, conformal field theory is way too complicated for me. Conformal field theory is interesting in lots of areas. In condensed matter physics, it's important for various reasons, some of which I understand. I understand why conformal invariance might be relevant near a second order phase transition, others that I don't understand. It's important in quantum gravity and string theory. And in string theory, I sure don't understand why it's particularly important, but that's no problem. But the other thing about quantum conformal field theory is that the mathematics is just very daunting. It's very hard. So it was way too hard for me. But there was another model that I should have been studying at the time, but I didn't, because it was invented by my thesis advisor. It's called the Summerfield model. In the Summerfield model, it's a model with a massless fermion coupled to a massive thing that looks like a gauge boson, except that it has a mass. And so the interaction looks like this. In 2 dimensions, that's not scale invariant. This coupling has the dimensions of a mass, actually, the way 2 dimensions work. But the point is that if this mass gets large, or at distances large compared to the Compton wavelength, to 1 over m0, you would expect to be able to integrate out these vector bosons and just get a 4 Fermi interaction, which is the Turing model again. Excuse me. So you expect this theory to be a theory of ordinary particles at short distances, but with a conformal sector that survives at low energies after all of when you're at sufficiently low energies that you can't make any of the heavy particles. And I thought about not this model, but about similar models when I got confused about what the Turing model was all about, and asked, well, what would this look like in the standard model? And the idea was that's unparticle physics. The unparticle physics is a world in which there's a standard model, but in addition to the standard model and whatever other interactions involved actual particles, there's a piece of the theory which is like the Turing model that is conformal and that survives at long distances after everything else has gone away because you don't have enough energy to make it. Now, the Turing model and the Summerfield model are not interesting enough to have much to say about this because they're what are called generalized free field theories. And I'm going to tell you much more about that in just a second. Not much more, because I'm not going to keep you for too long. But I think there's some interesting physics when you add fermion masses. But what I've been doing lately is thinking about a different class of generalized free field theories, which I find much more amusing and where I hope it's going to be a lot easier to understand when what happens when the mass is not 0. Because as soon as you put a mass in any of these theories, they become interacting, and then field theory becomes hard. So if I don't get to the punchline, which is very possible because you'll all be bored, you can look at a piece of this which is written up in physrev letters. So that'll give you some idea, at least, of what I'm thinking about if you want to look at the field theory in more detail. So what is the Schwinger model? Well, the N flavor, the Schwinger model, is just electrodynamics with N massless fermions in 1+1 dimensions. Very simple model. So it's obviously got some symmetry because these fermions all interact in the same way with the gauge bosons. In fact, it has an SUN cross SUN symmetry because I can rotate the left-handed and the right-handed flavors around. And classically, it also has fermion number conservation and a chiral fermion number conservation, but that's not going to survive. So when you solve, you can solve this model in lots of different ways. The way I want to think about is to replace the original fields that appear in the Lagrangian, psi and a mu, with functions of free fields. And in that case, that's what I mean by a generalized free theory. Everything, all of the correlators ultimately devolve into things that you can calculate using just free field theory, even though they may look complicated because this replacement is a little complicated. And in this case, the replacement isn't so terrible. And I'm going to focus on the fermions because I don't have time to talk about everything today. So what you do is you replace the original fermion field with a free fermion field times an exponential that involves a scalar field with mass m, which is the square root of which is e times the square root of n over pi, and a massless ghost. C is a massless ghost, which just means that its propagator has the wrong sign, and it's trying to produce negative probability. I don't know why negative probability is associated with ghosts, but never mind, that's another story. So the n=1 Schwinger model is a very famous model, which has been written about by many hundreds of people. It's the first example of what we would now call a Higgs mechanism, because the original gauge field gets replaced by a massive field, this B quantity. It exhibits quark confinement. The quarks are not free. It has anomalies like chiral anomalies like QCD that I'll come back to in just a second. And it also has chiral symmetry breaking. But it has no unparticle sector. And if you think about what I just said about the generalized free fields, it's kind of weird that it has no unparticle sector. There we go. Because suppose I look at a gauge invariant combination like the product of psi right star times psi left, kind of like a mass term in a fermion theory. If I just plug in the substitution I just described, I have this interesting thing that has some free fermions and some this exponential of these free fields. And if I now take that and calculate a correlator between two of these fields, O times its complex conjugate, so that I get something that I can calculate as non-zero in perturbation theory, then it goes to a constant as x goes to infinity. And that's kind of a miraculous cancellation between the effects of the free fermions, which go like 1 over x squared, because each fermion propagator goes like 1 over x in 1+1 dimension. And the ghost terms, this exponential of the C term here, when the dust settles, just contributes a factor of x squared, which cancels the 1 over x. So the only thing that's left is the contribution of the missing backslash there, latex error, sorry. Which goes like the exponential of some Bessel function of m times x. And that has, when x is very small, that goes to 1 over x squared because it has to reproduce the free field behavior of the product of the two fermion fields at short distances. Because this is a theory with only dimensional couplings. And so when the, if you go to distances large compared to 1 over those dimensional couplings, there are no interactions anymore. So it's got to look free. And it does, but that freedom, that limit comes not from the fermion skeleton here, but from the massive scalar field. So in this case, there are no massless particles. There's no unparticle sector, just a massive particle. And this is the same for all correlators. This miracle of the cancellation of the fermions and the ghosts occurs in all of the matrix elements. And it's a wonderful 1 plus 1 dimensional miracle, which I'm not going to explain at the moment, but which is really fun to see. The other consequence of this is that it tells you that this operator must have a non-zero expectation, vacuum expectation value. Because I can look at this correlator, which I can calculate just by summing Feynman diagrams. And I've told you that it's a constant times this exponential, this goes to minus infinity when, I'm sorry, this goes to 0 when x goes to infinity. And so this thing just goes to a constant. That means when I pull these two fields apart, it goes to a constant. But when I pull these two fields apart, they can't have anything to do with one another. So this must become the product of the vacuum expectation values when I pull them apart. And that means that the vacuum expectation values must be non-zero. So in fact, cluster decomposition tells you that the vacuum expectation value of this operator is this constant k times a phase, and you can set that phase equal to 0 because for massless fermions, that phase doesn't have any effect. For massive fermions, that phase is the phase that's associated with the chiral anomaly. So you might worry that the non-zero vacuum expectation value would be spontaneous symmetry breaking, which is impossible in one dimension because of Coleman's theorem, but it's not in this case because it's not spontaneous. The chiral anomaly breaks this chiral U1 symmetry, and that just comes from this Feynman graph, which, well, never mind the field theory, but that's what an anomaly does. So the effects of the anomaly, what this means is rather cool. It means that the effects of the anomaly in this theory, all of the effects of chiral symmetry breaking and everything else, can be calculated exactly just by summing up the Feynman diagrams and then using cluster decomposition. And so that's amusing and fun. And a totally nuts example that I like to think about is this one. This matrix element, this correlator between two O's, which would be 0 in perturbation theory to all orders, because it's two left-handed fields and two right-handed fields complex conjugated, is actually related to this one, except that I've made an error because there's a minus sign in here inside in the exponential. You can see that by putting in a couple of O stars far away and calculating the 4-point function, and then realizing that in this limit that you take them far away, you have this piece left over. It's kind of weird. So what does all this have to do with unparticle physics? And I'm about to stop because I'm late, I see. What it has to do with unparticle physics is that if you go to 2 flavors or more, the cancellation between the ghosts and the fermions doesn't work anymore. And those bilinear operators now have a non-zero anomalous dimension, and the theory has a conformal sector. And because I don't want to go too long, I'm just going to sort of skip to the punchline. These guys can't have vacuum expectation values. That would violate Coleman's theorem. But the product of 2 of them is an SU2 singlet, but it carries the U1 charge. So what develops a vacuum expectation value that you can calculate in perturbation theory is this product of 2 of them. And that, again, you can now calculate all correlators. But something kind of weird happens, and that is that you find that the difference between O1 and O2 star is exponentially suppressed in all matrix elements at long distances. So these 2 operators, O1 and O2, and their complex conjugates, only half of them survive in the low energy theory. And what I've been thinking about and trying to calculate in detail is now what happens if I add a mass term to the theory that is proportional just to these operators that are exponentially suppressed in the high energy theory. What I think happens is that the conformal theory survives, but the theory at short distances becomes interacting. And that would be interesting because it would sort of be a fun example to play with that's a little less trivial than the examples I know about. And I'm going to stop there and ask for questions because I've already gone over long. Because I spent so much time on boa constrictors and whatnot.
Yeah, this has been great. Do we have any questions from the audience? Remember, you guys can just raise your hand or unmute her.
I have a question. So, going back to I think like 3 or 4 slides, is this like I don't I think this might be a naive question, but like what is this like G-2? Like, does this have implications for that or no?
It's the same. I'm using the same technology, but no, it's not. What's nice about these 1+1 dimensional quantum field theories is that they're easy. The calculations are much easier than the calculations that go into G-2. By the way, my Charlie Summerfield, my thesis advisor, got his job because he actually calculated the second order contribution to G-2, the alpha squared contribution. So he was really good at this stuff. It would take me months to reproduce that. And now people do it routinely, but that's okay. It's a good question. We're all interested in G-2 because if this anomaly survives, it tells us something about the high energy part of the theory, the short distance part of the theory. And what I'm interested in here is the long distance part of the theory. It doesn't contribute directly to G-2 as far as I know, but probably one of the many papers that have been written about unparticle physics address this. So I'll think about it.
Thank you.
I should say the other thing about unparticle physics is the importance of coming up with a really cool name for your research, because the unparticle physics was popular partly because it was sort of an amusing idea, but partly because the name was so good. So
Are there any other questions, or are there other questions?
Yeah, is there something you can like tune the interaction to see what, I mean, you have the E coupling constant, like what's happening in terms of that?
see, the wonderful thing about this is, oh yeah, which I should have mentioned, this theory also, what should I say? No, there's no tuning, because there's only one dimensional scale. So E sets the scale of the mass of the scalar, which in fact is just E over the square root of pi. And there's no other mass scale in the theory. So there's no possibility of tuning. It's, if you change the value of E, that just means you change the your units. In the Summerfield model, you can tune things. And once you add a mass, then you can tune things, because then things depend on the ratio of E to the mass that you've introduced. And that's one of the really interesting questions. Everyone believes, and I think I see it in my way, that in this model, for a mass term of this special kind, there's a phase transition between, oops, you don't want to see that. A phase transition between what happens at long distances and, or rather what happens at weak coupling, which is for the mass very large compared to E, and what happens at strong coupling when E is very large compared to the mass. And that's certainly one of the things that I'm interested in understanding better.
Thank you.
The other, maybe one last thing to say is that the phys rev letter I wrote was stimulated by a paper that Sidney Coleman wrote long ago on the two flavor, on the massive Schwinger model. And so the way I described that paper was as answers to 3 puzzles that Sidney posed in that paper. And so that was kind of fun. Of course, the phys rev letter editors took out some of the fun comments about Sidney, but that's the way phys rev letters is. He was a wonderful character. I'm sorry you guys didn't get to meet him.
If you go back to the slide where you introduced the transformation, I'm trying to make some sense of it, because I mean, I don't know much field theory, but like kind of in the, if you were to put this on a lattice or something like that.
So which side?
The kind of substitution that you do.
Oh, that's an interesting question. People have certainly studied the Schwinger model on a circle.
Yeah.
And in fact, this is something I should have said. I'm specifically interested in infinite 1+1 dimensions, because what I'm interested in is the analogy with actual particle physics. There are lots of things that one can say about models of this kind that may be relevant to condensed matter physics and other things. Every once in a while, somebody will write an unparticle physics paper in the condensed matter theory world, but I've never quite understood them well enough. So.
Sorry,
Yeah, go ahead. Sorry.
Not mathematically, I don't know enough math, but what does the like partial symbol with the cross do it mean? Sorry.
Oh, sorry. Yes, that is the Dirac operator. So the slash just is a shorthand for d mu, gamma mu, where gamma mu are the gamma matrices, which in this case, in 2 dimensions, are basically just the Pauli matrices. Sorry, I should have written all of that down. But what I was trying to avoid was getting bogged down in notation. In fact, I purposely didn't define my notation because I didn't want to encourage you to look for all of the sign mistakes I probably made.
Thanks.
All right. Well, it's approaching 5:40, so we'd probably like to wrap up. But maybe Professor Georgi, if you have any final words of wisdom, and yeah.
Well, one comment is it's fun to think about these when you start to learn field theory. It's fun to think about these 2D theories because they are easy, and they give you some feeling for some of the complicated stuff that you're struggling with. So that's fun. I guess apart from that, I think the thing that I didn't say, but which I could have, was that if you're lucky, you'll get to hang out with some of these incredible characters that will make you feel really stupid at times. But that's good. That's an opportunity. There was a time all of you have to remember how much better you are at all of this stuff than normal people. And you also have to remember how much better Ed Witten is than you are. And that's okay, right? It's the point is that Ed is unbelievable in many dimensions, but the intelligence is a space with a large number of dimensions. And all of these characters that I've been talking about are way the heck away from the origin in some direction or other. It's just that there are lots of different directions, and you should find your own. You should spend a little bit of time thinking about what your intellectual base camp is, and learn from there, grow outwards.
Awesome, Professor Georgi, thank you for that perspective and for joining us today. And I also like to thank everyone else for coming today and for tuning in throughout the past year. It's been a ton of fun.
Yeah, thanks so much. And thank you guys for organizing this. It was amazing.
Absolutely. I want to just throw one more thing out there. So this is the last Chilloquium of the school year, but we'll be transitioning to a new SPS board in the coming weeks, and they should start running a Chilloquium series over the summer. So look out for word of that around June. Thank you, everyone.
Take care, everybody.
Thank you so much.
Thank you.
Thank you.